Okay, welcome to Physics 1151, Section 102. This is our first lecture of the semester, and we're going to start off by beginning our treatment of fluids, which corresponds to Chapter 14 in the text. Before we do that, I want to go over just a couple little points related to the lectures throughout the semester. So what we're going to do here is there's going to be 4 recorded lectures each week. And you'll watch these on your own. And they will cover the content of that week. So the Mondays where we meet synchronously, there will not be a lecture on that day, but rather we will cover problems that you want to go over, examples in these 4 lectures. So you can work on these anytime that you want, but we will meet on Mondays to go over problems. So Mondays are not required. The exceptions are we will have a few unit exams during the semester, if you look at the syllabus, and we will have occasional quizzes on the homeworks. Those will all be held in class on Monday, and you do need to be on Zoom during those times. So all of this is covered in the syllabus, so I encourage you to read the syllabus and to watch the short YouTube video related to that, and stop by during office hours if you have any questions. So each set of notes will begin with the topics covered. And these are the topics that we're covering in this set of notes. At the bottom will be the required reading in the text corresponding to these notes. And then there will be the relevant assignment. And so, for example, the first assignment, which you will upload to your folders on Google Drive on the 27th, and that's all discussed in the syllabus. So assignment 1 will be due on the 27th of January. The next thing that we'll have in each set of notes is the learning objectives. And so if you notice up here, it says after completing the notes and the examples, along with homework 1 and the relevant sections of the book, you should be able to complete the following tasks. And when I make up exams, I take my exam questions right out of these. Now, note that the notes are not self-contained. You need to read the relevant sections of the book. These lectures are a supplement to the book, not a substitute for reading the book. And so you should work out the homework problems, you should work out the example problems in the book and in the notes here, and then afterwards, when you're gauging your understanding for exam purposes, this is what you should be able to do. So let's get started here. We're going to be covering fluids, which is chapter 14 in the text. You spent a lot of 1150 covering solids. And solids are just objects that maintain a fixed shape. They're incompressible. They're rigid. And you discuss pushes and pulls on the solid. You discuss quantities such as mass and kinetic energy and potential energy. What we're going to cover now is we're going to move on and cover fluids. And what we're calling fluids are objects that can flow. And there's 2 types of fluids. There's liquids and there's gases. And these both differ from solids because they're able to flow, and therefore they can take the shape of their container. For example, ice cubes. So the difference between solids and liquids can be summarized in this figure right here. So solids, which aren't shown, are very rigid. The molecules are tightly packed, and they're only able to vibrate, but they're not compressible. Very dense, compact, and they don't flow. Fluids, on the other hand, liquids and gases, are able to flow. And so here's a liquid, and a liquid and a gas are similar in many respects, but they're different in some. So The liquid, the gas molecules are weakly bound to one another, and they're close together, but they're not as tightly packed as a solid, and so they're still able to flow relative to one another. Whereas a gas, the molecules are spread out far enough that there really aren't very strong, if any, attraction forces on them. And you can think of them like a bunch of little balls bouncing around in a container which don't interact. And so the difference between the two is the fluids are very difficult to compress. If you've ever tried to compress a liquid, you can't compress it, and it's incompressible. Whereas a gas is very easy to compress, and that's just because the molecules aren't so tightly packed, and so the material can easily be pressed down and compressed. So liquids and gases are similar in many respects, but liquids have stronger attractive forces. The molecules are closer together, and they're therefore incompressible, whereas gases are. So how do we describe a fluid? Well, with solids, we use quantities such as mass and force to describe what happens to a solid. With fluids, we use variables such as density and pressure. And so density is the fluid analog to mass. It's the mass per volume, whereas with solids, we discussed the object's amount in terms of mass. Similarly, with objects, we discuss forces. With fluids, we use this variable called pressure, which is the force per area exerted by the fluid on the container. And then there's some other variables like temperature and velocity, which have similar meanings as if we go back and forth between solids and between fluids, liquids and gases. So the first variable that we'll discuss here is what's called density. And density is equal to the mass per unit volume of the fluid. You can think of it as how packed together is the fluid in the material. And since the mass has units of kilograms and the volume has units of meters cubed, the density, which is the mass per unit volume, has units of kilograms per meter cube. And this is a property of the material, of the fluid, the substance. It doesn't matter how much fluid, how much water is in a container of milk. It's the same density. Water, it's a property of the water, or in general of any fluid. So it's an intrinsic property of the material. Now there's several different units that are used to describe mass and volume. So the standard unit is kilograms per meter cubed, at least in SI units. But you may often see it written as grams per centimeter cubed, or in other units. And so in this course, we're going to have to work back and forth between various units. And so here's a simple example involving water. And so water, we know, has a mass of 1 gram per centimeter cube, which means in every centimeter cube of water, the mass is always 1 gram. And we want to convert this to units of kilograms per meter cubed. Okay, so how do we do this? You may have done some of this in 1150 or chemistry classes, certainly. We're going to be doing a lot of it here. So what we want is we write what we have down. So we start off with units of grams per centimeter cube. And we want to go to units of kilograms per meter cubed. So we need 2 conversion factors. We have to go from grams to kilograms. And so we know that 1 kilogram is equal to 1,000 grams. So we need that conversion factor. And then we're going to have to go from centimeters cubed to meters cubed. So we need a conversion relating centimeters to meters. And we know that 1 meter is equal to 100 centimeters. Okay, so the next step is how do we string these conversion factors along to get from where we're starting, which is grams per cubic centimeter, to where we want to end, which is kilograms per meter square. And here's where dimensional analysis is very helpful. So we're starting with grams per centimeter cubed. So we want kilograms in the numerator, and we want to get rid of grams. And so we need to apply 1 kilogram is 1,000 grams. Now we want the grams to cancel out, so we put the 1,000 grams in the denominator, and we want to end up with kilograms, and so we put the kilogram in the numerator. And then the units of grams cancel, and now we have grams per centimeter cubed. The next thing we need to do is we need to get rid of cubic centimeters, and we need meters cubed in the denominator. So we're going to use our conversion between meters and centimeters. 100 centimeters is 1 meter, and we apply that factor. Now, one common mistake that students make is they say 1 meter cubed is 100 centimeters cubed. No, that's not true. You need to cube both dimensions, and so we take this conversion factor, 100 centimeters is 1 meter, and we cube it because we have to apply it to all 3 dimensions. And so now if we look at our dimensions, the centimeters cubed cancel, we're left with kilograms per meter cubed. And now we look at the numerator, we have 100 cubed is 10 to the 6 divided by 1,000. And the 1,000,000 divided by 1,000 is 1,000, and we get 1 cubic centimeter is equal to 1,000 kilograms per meter cubed. And so it's very important in the course to be able to convert between different units, and we're going to do this quite a bit on homeworks, exams, and in lecture. So study this example, and we're going to be doing a lot more of it. So here's some examples of some densities of fluids, and the mass density, we use the symbol rho, which is a Greek P-looking character. And so we look at rho, and the densities span about a factor of 10 to the 5, ranging from mercury, which is one of the densest fluids, to helium gas, which is one of the most dilute gases. And so they can vary by a factor of 5. And liquids are more dense than gases just because the molecules are packed more closely together. So if you look at water, water's 1,000 kilograms per meter cubed. Most liquids are not too different from water in their densities. Oil's a little less dense than water, which is why oil floats on water. And then you have the alcohols, which are less dense. And you look at seawater's a little more dense than pure water, and that's also why we tend to float a little bit on seawater versus fresh water. The gases are much, much less dense, on the order of a kilogram per meter cubed for air. And so liquids are always much more dense than gases. Another type of problem that we're going to be doing a lot in this course, or we're going to be doing ratio problems. And I'm not sure if you've done these in 1150 or in chemistry, but I want to do an example to illustrate. Before we do it, what a ratio problem answers is you have a relationship between a dependent variable and an independent variable. And one simple example is kinetic energy is 1/2 mv squared. Okay, so the dependent variable is kinetic energy, K, and speed is an independent variable. And so a ratio problem answers a question such as, by what factor does the kinetic energy increase if we double the speed of the body? And so if we double the speed, and since kinetic energy is related to the square of speed, the kinetic energy will increase by a factor of 4 when we double the speed. So that's one simple example of a ratio problem. So the first example of what we're going to do is we've got 2 cylinders, and we put them side by side, and we have equal heights of fluid in both cylinders. So they're both the same height, but the first cylinder has twice the diameter of the second cylinder. So the diameter of the first is twice the diameter of the second. We also, let's just for fun, put different fluids in each. And so the first cylinder will have water, which has a density of 1,000 kilograms per meter cubed. And the second one has oil. which has a density of 900 kilograms per meter cubed. Okay, and the question is, what is the ratio of the mass of water in the first cylinder to the mass of oil in the second? In other words, what is M water divided by M oil? Okay, now what I'd like you to do is I'd like you to stop your video here and try to work this example out before looking at the solution that we're going to cover next. So we're going to go into it in detail, but take a time out here and try to work through this on your own. All right, so assume that you've tried to work it out and you're back. Let's take a look and work out the solution here. So the first step that we always have to do in these ratio problems is we need one or more equations which relate what we're trying to find, which in this case is mass, to the variables that were given. Okay, and so we know that the mass is equal to the mass per volume, which is density times the volume. And we're not given volume, but we're given the dimensions of a cylinder. And so we know that the volume of the cylinder is pi r squared, where r is the radius, times the height of the cylinder. And we know that the radius is equal to half the diameter. And so the volume of the cylinder is pi times d over 2 squared times h. And so that multiplied by density gives us mass. Okay, so this relates mass, which is what we're trying to find, to the variables that were given: density, d, the diameter, and the height of the fluid. Now, we're not given numerical values for each of these variables in the problem, but we don't need them because all we're trying to do is determine the ratio of the two masses if we know the ratios of the diameters. In this case, if we go back here, we know that the second cylinder has half the diameter as the first, so D1 is 2 times D2, and we know that the density of fluid in the first cylinder is 1,000 over 900. So in this case, we do know the numerical value, but the diameters we don't know, but we don't need to because we're taking ratios. Okay, so now we have an equation which relates what we're trying to find, which is mass, in terms of the variables that were given. Okay, the next step is we write this down, we write this equation twice. We write it first for the first cylinder, and we're going to use all W's for subscripts because that's water. And so the mass of the water is the density of the water times the volume of water. And I've used W's for subscripts to denote that we're talking about the cylinder that contains water. And we do the same for the mass of the cylinder containing oil, the density of oil times the volume. And now we have this ratio. Now all the constants will always cancel out when we take ratios. For example, pi is in the numerator and the denominator, that cancels. This 2 cancels because it's in both. And what I always like to do is I always like to write this in terms of the ratios of each of the individual factors. And so the mass of the water divided by the mass of the oil is equal to the ratio of the densities times the square of the ratio of the diameters times the ratio of the heights. And you don't have to do it like this, but it makes it easier, at least I think it does, when we plug in the individual ratios. Okay, so don't plug in numbers yet. Okay, then the next step is what do we know? Well, we know that D water is twice D oil. In other words, the diameter of the cylinder containing water is twice the diameter of that containing oil. So I can write D water over D oil is 2. I know that the ratio of the heights is 1 because they're both filled with the same height, so I put a 1 here for the ratio of the heights. And the ratio of the density of water to the density of oil is 1,000 over 900, and that's 10 over 9. So now I have my ratio of masses expressed as 3 ratios. And then you just multiply these all out, and this is equal to 40 over 9, which is about 4.4. And so what this says is that the mass of water in the first cylinder is 4.4 times greater than the mass of the oil in the second cylinder. And so finally what you should always do, but some of us get lazy, myself included, and don't always do this, is you should look at your answer and make sure we didn't screw up. Okay? So what this says is that the mass of the first one of water is twice as great as the mass of oil. Well, does that make sense? Well, let's look. It depends on the ratio of the square of the diameters, and we know that the diameter of the water cylinder is twice the diameter of the cylinder containing oil. And when you square that, that's 4. So based on diameters alone, we should have about 4 times more mass of water than we do of oil. Okay? The heights are the same. And then the density of water is a little bit greater than the density of oil. And so this ratio should be a little over 4, and it is. It's 4.44. And so I always like to, well, I should check my answers every time, and I usually do, but sometimes I don't. But you should always check your answers when you're done to see if they make sense. And so this is an example of the methodology used to do ratio problems, and we're going to be doing a lot of these during the course of this semester. So so far we've covered variables such as density, mass, volume. Another variable which is very important when describing liquids and gases is a variable we call pressure. We've all heard this. We put pressure on a wound. So we have our fingers bleeding. We apply pressure to stop the bleeding. Atmospheric pressure. We've heard the word a lot. And so what pressure is pressure is defined as the force per unit area exerted by the fluid on a surface. Okay, so with solids we dealt with force. With fluids we deal with the force distributed over an area, or the force per area. And we call that variable pressure. And we use the symbol P to describe pressure. Okay. So the force has units of newtons, area has units of meters square, then pressure, which is force per area, must have units of newtons per meter square. And we give that a special name called the Pascal, named after Blaise Pascal. I think he was a chemist. And so pascals are the units, and we denote them in shorthand as PA. So PA is a Pascal, where 1 Pascal is the same as 1 Newton per meter square. Now there's a couple differences between pressure and force. So force is just the force, how hard we're pushing or pulling, whereas pressure is the force just per area. Another important difference is that pressure is a scalar. It doesn't have it's not a vector, it doesn't have a direction, whereas force is a vector. We denote it as a quantity, a numerical value, and we denote it with a direction. And so pressure is a scalar, force is a vector. Pressure has a wide variety of units, some of which are pretty bizarre. So we're going to be primarily using the unit of a Pascal, which is Newton per meter square. If you're dealing with air, processes done at air, a lot of times chemists or atmospheric scientists will put pressure in units of atmosphere. Okay, and what that means is that at sea level, the atmospheric pressure is 1.013 times 10 to the 5 newtons per meter square, or in other words, 101.3 kilopascal, and that is atmospheric pressure. And so sometimes it's more convenient, instead of dealing with pascals, to deal with units of atmospheres, where atmospheric pressure, 1 atmosphere, is the same as 101.3 kilopascals. And it turns out that the pressure decreases with altitude, and at Boone's altitude, it's about 90 kilopascals, or a little less than 90% of that at sea level. Okay, so this is one unit of pressure, is atmospheres. If you're dealing with vacuum pumps, they'll have units of torr often on the vacuum pump, and that's kind of a weird unit. 1 torr is 1/760 of atmospheric pressure, or 133 newtons per meter square. We're not going to do much with torrs, but in other subjects you may see this, and so here's a conversion factor. If you've ever heard of barometric pressure used by meteorologists, they'll use bars where 1 bar is the same as 100 kilopascals, which is roughly the pressure at sea level. And they'll deal with millibars, which is 1,000 bars. We're not going to do too much with bars. A very common unit, if you've ever used tire gauges or compressors, is what's called PSI, or pounds per square inch. And so atmospheric pressure at sea level is equal to 14.7 pounds per square inch, which means the pressure of air pushing down on anything at sea level is 14.7 pounds of force per every square inch of surface area, or 14.7 psi. Okay, and so 14.7 psi, or pounds per square inch, is the same as 1 atmosphere, is the same as 1.013 times 10 to the 5 Newton per meter square. And so we're going to have to go back and forth often in the course between some of these units. The main thing is that you may be given other units in a problem, but if the other variables in the formula that you're going to plug these in have SI units, we need to always convert these pressures to units of pascals, meaning newtons per meter square, before plugging them into the formula. Okay. So we say that pressure doesn't have, it's not described by a vector. In other words, equal pressure is the pressure is the same in all directions, and it's basically equal to the force per area that the fluid exerts on the container. Here's an interesting example, a YouTube video, so let's watch this, that shows how pressure on a fluid can exert a force.
So we have an open can here, and the air, the atmosphere that's being pulled down by the gravity of the Earth is pushing on the outside of the can. But since this is an open can, the air inside, that same air being pulled down by the Earth's gravity, is pushing out. And then we have this kind of equilibrium here where nothing happens to the can. Let's think about those molecules inside of the can and what they're doing. So we have molecules of air, the red are oxygen, blue nitrogen, there's some argon, carbon dioxide, and water vapor. And as they move around, when they're hitting the side of the can, they're creating pressure. That's the air pressure. And that's pushing on the can from the inside. Of course, on the outside, we have the exact same pressure, and that's pushing on the can. Every time those molecules collide with the can, they create pressure as well. So let's think about liquid water. We put a little bit of water in the can, and it sits at the bottom of the can, and then we have the air above it with those gas molecules moving around. But if we start heating those water molecules, so here we have, as a liquid, these molecules are moving around, but they're pretty much staying together. They're not getting too far apart. If we raise the temperature up, it will change from a liquid into a gas, and the water molecules will spread out. When they do that, they'll push all of those air molecules out, and all we'll have inside of the can is water vapor. Let's see that happen. The temperature increases. You can see the water molecules are spreading out, and they'll force the air out of the can, leaving just water vapor in the can. So now we flip the can over, put it in water. That seals the top so no air can get in, and we've cooled the can. And all that gas, that water vapor in there, changes back to a liquid very quickly. That's important because as a gas, the water molecules were hitting the side of the container and creating pressure. We still have air on the outside, molecules hitting the side of the container, creating pressure, But on the inside, we don't have the gas anymore. We have a vacuum because we've sealed the top when we turn the can over. And because of that, air pressure on the outside crushes the can.
So, what's going on here?
Hi everyone, I'm Emily, and today we are doing the science behind the can crushing experiment. For this one, you're going to need a large bowl of ice.
Sorry about that. So, the pressure, if we look here, the pressure of the gas molecules, or in this case the liquid, exerts a force on the walls of the container. The force per area is the pressure, and that in this case it's due to the weight of the liquid pushing on the container. But the container stays rigid, so that means there must be an equal and opposite pressure exerted on the container for downward, and so this is in equilibrium. And the same with the gas. In this case, the pressure isn't created by the weight of the gas with gases, but it's due to these molecules bouncing around, and when they bounce, they exert a force on the container, and the force per area is the pressure. And the greater the density of the vapor in here, the more molecules are colliding per second with the walls of the container, and the greater the pressure they exert. And so the air on the outside is pushing back on the walls of the container, and so you have two equal and opposite forces due to the pressure on the inside of the container and the pressure on the outside. Now, when you heat up the water inside the can and then you flip it over and you cool it, that creates a vacuum because the water condenses, and now the pressure on the outside is greater than the pressure on the inside, which means there's a net inward force exerted on the container, and that crushes the container. And one example of this is when you go up in an airplane and the pressure changes suddenly, then the air pressure on your ear quickly decreases and your eardrums expand outward because an outward force is exerted on the eardrum, and sometimes you feel your ears pop as you're going up and down in altitude. And so that's the same thing. And so in this case, when the gas is cooled and it condensed, then the vapor pressure is less than the pressure outside, and so there's a net force crushing the can. And it's a fun little exercise to do. You can heat the can up on your stove. Then you take it, you quickly flip it over into a bowl of cold water, and the can will collapse. Make sure to wear gloves because the metal's a good conductor. And so when you take the can off the stove, you don't want to burn your hands while you're flipping it over. But this is a nice little example of pressure. Okay. Now, the pressure is the same in all directions, and we're going to see that in a minute, but let's first do this example, and then this will lead into where we're going. So here we have a 200-pound man, and his feet cover an area 500 square centimeters, and he's standing on the floor. Okay, and the question is, what is the pressure exerted on the floor by the man's feet? And so the pressure is the force per area. So stop your video and try to calculate this before moving on, and then we will move on to the solutions. Here's a couple conversion factors. We know that weight is equal to m times g, right? We learned that in 1150. So 1 kilogram times 9.8 meters per second means that the weight of a 1 kilogram object is 9.8 newtons. Okay, now in British units, that's 1 pound has a weight of 1 kilogram, which has a weight of 9.8 newtons. 1 kilogram is the same as 2.2 pounds. And so 9.8 newtons must be the same as 2.2 pounds. And so a conversion factor of 1 pound is 4.48 newtons. And so we need to convert 200 pounds to units of newtons. Then we need to convert centimeters square to meters square. And we do that. And we convert pounds to newtons. So 200 pounds is 891 newtons. And the area, 500 square centimeters. We use the conversion factor 100 centimeters per meter. We square it because it's 2 dimensions. And we get that the area is 0.05 meters square. And we take force per area, and we get that a 200-pound person exerts a pressure of 1.8 times 10 to the 4 pascals on the floor. So that's the pressure exerted by this person on the floor. Now here's an interesting result. This pressure, 1.8 times 10 to the 4, is only about 20% of atmospheric pressure, which is the pressure exerted by the air on the floor. And so air pressure must be really high, right? It's about 5 times larger than the pressure exerted by a 200-pound person on the floor. And so the question is, why doesn't air crush us? I mean, that's a pretty high pressure. So to do this, orient your hand vertically, or horizontally, I mean. So if the pressure is much, much higher than 200-pound person, why isn't this crushing our hand? Well, the atmosphere, the answer is that the pressure exerted on our hand by the fluid, the air, is the same in all directions. And so there's pressure from the air above our hand pushing downward, and the pressure exerted by that is 1 atmosphere. But there's also pressure from the air below our hand pushing upward. And the two pressures must balance because our hand is not accelerating. And so in other words, the pressure of the fluid is the same in all directions. The upward pressure from the fluid below us at a given point is the same as the downward pressure from the pressure above. And it's the same in both directions. And we can flip our hand 90 degrees, and our hand is not accelerating, which means the pressure due to the air on the left pushing it to the right, our hand, must be the same as the pressure from the air on the right pushing our hand to the left. In other words, the pressure is the same in all directions. And that's why we don't need to describe it by a vector. It's the same at a given point in the fluid in all directions. Otherwise, our hands would be crushed due to the pressure from above. So pressure is force per area. Now there's 2 contributions to the pressure. With gases, we go back, where's my slide? Right here. The gases, the force per area on the walls of the container is largely due to the molecules bouncing around and exerting forces on the wall. In this case, gravity has very little effect on pressure. In other words, the pressure at the bottom of the container is not any higher than the pressure on the top because there's no more weight on the bottom than there is on the top. And so with gases, in general, the pressure is constant throughout the container. And so when we deal with a can of gas or a can of vapor, the pressure is pretty much uniform inside the container. This is not true if we have a column of atmosphere. The pressure decreases with altitude, as we know. But with a small enough volume, it doesn't really change with height. It's the same uniformly. Now, with a liquid, it's different. The pressure here, the force per area on the walls of the container, is due to this weight sitting on top of the bottom wall here. And so this pressure decreases as we go upward because there's less weight above a given point. So the pressure is greatest at the bottom because there's more weight of the fluid above it. And the pressure inside the fluid does tend to decrease with height because there's less weight above that point. And so with liquids, the pressure can change dramatically with altitude, as if you've ever done any snorkeling or scuba diving, as you go down underneath the water, the pressure increases greatly as you go to greater depths than at the surface. But with gases, you've got to go quite a bit up and down to notice any differences in pressure just because the density is so low. So the last thing we're going to cover here today before ending is we want to get an equation which describes how the density of a fluid varies with depth, okay? And like I said before, any of us who have went swimming, or I don't know if you ever took swimming lessons as a kid where they made you go into the bottom of the pool and pick up a brick from the bottom and bring it back up. If you've ever went to the bottom of the pool or done scuba diving or anything, you know that the pressure increases dramatically with depth in a fluid. And so what we want to do is we want to derive a mathematical equation which describes how pressure changes with depth of the fluid. We're going to make a couple assumptions here. We're going to assume that the fluid is incompressible. In other words, the density of the fluid is constant. Okay? Well, this is true for liquids, but it's not true for solids. So the equation that we're going to derive works very well for liquids. Don't use it for solids. Solids are compressible. So we're going to assume constant density, and then we're going to assume that the fluid is in what's called hydrostatic equilibrium. In other words, the sum of the forces acting on the fluid is zero. The forces pushing up at a given point on the fluid are the same as the forces pushing down. And so that's static. Hydro is fluid, and so this is what's called the hydrostatic pressure. So let's calculate the equation here. Okay, so let's consider a given element of fluid here, and the depth at the bottom of this little parcel of fluid is located at distance d below the surface, and at d equals 0, that's at the surface. Okay, and the fluid has a cross-sectional area A, where A could be width times length if it's a box, and it has a depth d. So at the top of the fluid, there's a force pushing down at the top, which is pressure times area, and that pressure is due to whatever the air pressure is, or whatever the pressure is at the top of the fluid, and we denote that as P0. And if the fluid is open to if it's open to air, this is just atmospheric pressure times area, and that's the force exerted on the top of the fluid. At the bottom of the fluid, there's an upward force from the air below, from the fluid below it, the water below it, and that's equal to whatever the pressure is at this point, P, times the cross-sectional area. And so there's an upward force exerted by the fluid below on this point, and there's a downward force exerted on the top of this parcel due to the air above it. And there's an additional force exerted on the fluid due to its weight, m times g, where m is the mass of this little parcel of fluid, and g is the gravitational constant. And if we choose the upward direction as positive, there's an upward force P times A, and then there's two downward forces. Here's our free body diagram. mg is the mass is the weight of the fluid, and that's negative because it's pointing downward. And the pressure at the top times A is also a downward force, and that's P0A, and that's also negative. And if we're dealing with statics, the sum of the forces must be 0 in the y direction, the vertical direction, so we set the three of these forces equal to 0. Okay, now the next thing we have to do is we want to write mass in terms of the density of the fluid times the volume of this parcel of fluid. And so the volume is equal to the area times the height. So area times d is the volume, rho is the density, and we substitute this in for the mass, and our Newton's second law becomes this equation right here. Okay? And now if we notice area is in all three of these terms, so it cancels out. We can divide both sides by A. In other words, it doesn't matter what area we choose, and we get this as our equation. It's the pressure at some depth D is whatever we start off at the top, P0, plus the increase in pressure with depth. And this second term is the pressure at a given depth D due to the weight per area of all the fluid above it. So the first term, P0, is the pressure at the top. And then this second term, rho times G times D, is the pressure due to the weight of all the water above a given point D. And so what this says is that the pressure at a given depth D increases linearly with depth. If we double our depth in the fluid, the water pressure here doubles, and then to that we add the contribution at the top. And so this is a very important equation. I encourage you to write this on your cheat sheet for exams. You're going to be given a cheat sheet. We talked about that in the syllabus. We'll talk about it more. This is a very important equation because if we know the pressure at the surface, and we know the depth of the fluid, and we know the density, we can get the pressure at any depth of the fluid using this equation. Okay. So here's a summary. For liquids that are incompressible, the pressure increases linearly with depth, and it's given by this equation. Pressure is the pressure at the top of the fluid plus the pressure at a given depth due to all the fluid above it. And this is what's called the external pressure, P0, and the second term is the fluid pressure. Okay, so let's end by doing one example. So again, I encourage you to stop your video right here and to try to work out the example before moving on and looking at the solutions. So we have a diver 100 meters below the surface of a lake. And what we want to determine is what's the pressure exerted on the lungs of the diver due to the water above the diver, which is your fluid pressure, and the atmospheric pressure. So what we want to do, we know the depth, D is 100 meters, and we know the density of water is 1,000 kilograms per meter cubed. So if we go back to this equation, we know depth, we know the density of water, and we know G is 9.8. So we can calculate the pressure due to the fluid above the diver. And we also know atmospheric pressure is 1.01 times 10 to the 5th newtons per meter square. Okay, so let's calculate. So we plug in the pressure at the top of the fluid as atmospheric pressure, 1 atmosphere, which is 1.01 times 10 to the 5th newtons per meter square. The pressure of the water above the diameter is the density of water times G times the height of the fluid column above it, which is 100 meters. And we plug all these in, and we get that the pressure of the liquid is 9.8 times 10 to the 5th pascals. And we can convert that to atmospheres. That's 9.7 atmospheres. And so the total pressure on the diver is the pressure at the top of the fluid, which is atmospheric pressure, plus the fluid pressure, is 1.08 times 10 to the 6 pascals, or 10.7 atmospheres. So what this means is that the pressure on the lungs of a diver at a depth of 100 meters, which is about 328 feet depth inside the underwater, is 10.7 times greater than atmospheric pressure. And if you look at most of the contribution to the pressure on the diver is due to the water, and only a smaller contribution is due to the air above it. And so this is one example of applying this equation of pressure with depth to calculate the pressure at any point in a liquid. So I think we're going to stop here. And so we will resume with these notes tomorrow. So have a good day.